All right. Anyway, welcome back. Nice to see you all again. So this is our final week. What we got is, today and tomorrow will be more or less ordinary class meetings, and then Friday will be our last test of the semester, and then we also have the final exam. So I hope everybody is clear. The test on Friday will include all topics for the whole semester, including what we're doing today and tomorrow. If all goes well, you may be able to finish your entire checklist on Friday, and then you won't have to take the final exam. More likely, you will still have some things remaining to be checked off after Friday's test, and so you will come to the final exam, and that will be your one last chance. Some people probably will come to the final exam and only need to do 2 or 3 questions. Others of you will need to spend a long time, but the final exam is scheduled for 3 hours, so you can have a lot of time to do the final exam. Our test, on this week on Friday is just a normal 50-minute test.
Can you get the exam grades for just Friday before the final?
Yes, yeah. So I'm gonna try to grade this Friday's tests, immediately by the end of the weekend, so that you'll know which ones you need to do for the final. And like I said, some people probably won't have to do the final at all. All right. Any other questions about that? Great. So we have there's one more thing on the list, but actually we have sort of, and that's the sorted edges algorithm. But we have one more day, and I decided to add in another topic. So there will be a new topic on the list, which I'll tell you about it when we get there. But this, what I want to talk about today is the sorted edges algorithm, and then probably a little bit of this new thing. So I thought it might be fun to just do this whole thing on this, something like a worksheet that I've made up. It's not really, not too much like a worksheet, but just because the examples of these things, I have fairly complicated graphs like this, which are real pain to copy down, and you might mess it up just from the copying. So I printed them all out. By the way, we do have homework due tomorrow. I handed out printed copies last time. If you weren't here last time, I have more that you can take on your way out. All right, so I hope everybody remembers that we are talking about the traveling salesman problem. I hope you all talked with your grandmas about it over Thanksgiving dinner. The traveling salesman problem, remember, is you start with a weighted complete graph. That's what this is. And your job is to find a Hamilton circuit with smallest possible total weight. The idea behind this, this is written, this example is written totally abstractly, but the idea is you could imagine these 5 places are like different locations that you have to visit, and the numbers represent the distances from one to the other. And the goal is to find the best route to visit all 5 places and end up where you started. Or maybe you could say one of these places is like your home, and then there's 4 other places you have to go to. Anyway, you're trying to find the best possible route to visit all these places and end up where you started. And we have discussed 2 methods to do this so far. The first is the brute force method, in which you just write down all possible routes and just calculate the total weights of each of them. This is a real pain to do. It's not so bad if you have only like 3 or 4 vertices, but if you have more than that, you basically never want to do it that way, the brute force method. You don't have to think too hard to do the brute force, but it will take you a long time. Last time we talked about the nearest neighbor method, and today I want to talk about the sorted edges. If you weren't here last time, that was the nearest neighbor, although this is just a totally different method. It has nothing to do with the nearest neighbor, so you don't need to know how to do that in order to do this. But anyway, I'm going to try to just write down here how to do the sorted edges algorithm. It's pretty straightforward. Here's how we do it. We write out all the weights. The weights, remember, are those numbers in order in a big list. All right? So in this example, we can just do this immediately in this example. Write out all the weights in order in a big list. The weights are the numbers. So when looking at the graph over there, I see a 1 and a 1. By in order, I mean like in numerical order, lowest to highest. So I see 1 and 1. I see a 2. Now you have to be careful and make sure you get them all, but maybe I'll just sort of like underline them as I go. I see a 2 here, just to make sure I get them all. No other 2s. I see 2 3s, a 3 and a 3. I see 2 4s, I believe. A 4 here and a 4 here. Unfortunately, if you miss something, it'll screw the whole rest of the procedure. So you may want to double check, make sure you're getting them all. I see 2 5s, 1 there and 1 there, and then a 7, and that's it. All right? So these are all the weights in order. This actually is why it's called the sorted edges algorithm, because these, the weights represent these edges. So this list here is why it's called sorted edges. Sorted because I wrote them all in order. I hope I didn't miss any. Am I doing okay so far? I see some looks, the kind of looks when I mess something up, but maybe I'm all right. Okay, you write out all the weights in order in a big list. And now, to build your Hamilton circuit, you just choose edges. Choose the cheapest edges in order. And the rule, as usual, when building a Hamilton circuit, never make a subcircuit and never make a three-way intersection, because such things are never allowed in a Hamilton circuit. All right? You just choose the cheapest edges in order. So I am going to, now you could scribble on the original picture, but just to avoid messing up the original picture, I'm just going to redraw. I'm not going to redraw everything, but just the vertices here, right? And when I say choose the cheapest edges in order, I would start with the 1. Now there are 2 1s, and I'm just going to choose them both. So I take the 1 here, which is like that, and this one here, which is like that, all right? And you are, as you're choosing them, you're not trying to make a circuit. You just choose any old edges. They don't have to be connected with each other at all or anything like that, all right? And you don't imagine that you have a specific starting point and ending point over here. I just pick the 1 and I pick the other one because those are the cheapest available. All right, next is the 2. You should ask yourself, am I allowed to pick the 2? Because I did say there are rules here. You can never make a subcircuit, and you can also never make a three-way. So am I allowed to pick the 2? The 2 goes like this, and I think that does fit in nicely with what I have already. It does not make a three-way intersection, and it does not make a subcircuit. So I will also pick the 2, all right? Okay, what about the 3s? I have a 3, there's 2 3s, one going A to C and one going E to B. Can I use the 3 going from E to B? I say, no, actually that's not allowed. I mean, you might be tempted to draw it in there, but actually that makes a three-way intersection at B. So this 3 is not allowed, because this one makes a three-way, which is not allowed in a Hamilton circuit. What about the other 3? I guess it's slightly ambiguous which 3s I'm talking about, but what about the other 3? That one goes from A to C, and you should ask yourself over here, is that allowed to put that one in? Does it make a three-way intersection? It does not. Does it make a subcircuit? I think actually that does make a subcircuit. If I put this in here, now I have closed up this circuit here, but I never went to E, right? So that actually is a subcircuit. You should not use that edge either, because this one makes a subcircuit. Remember, a subcircuit means you created a circuit without actually going through the whole picture. It only goes through some of it. All right, so I cannot use the 3. All right, now we just go through the rest of the list. Try to use a 4. There's a 4 over here, E to D. That's not allowed because that would make a three-way at D. So that 4 is no good. The other 4 is here, E to C. And I think this one is legal, right? if I put in an edge here, E to C, that does not make a three-way intersection, and it also does not make a subcircuit. I don't know if sometimes people get worried about, like, what about this little triangle here? Doesn't that count as a subcircuit? The answer is no, because this is not a real circuit, because that right there is not a real vertex. There are only 5 vertices in this graph. This is just where the lines are crossing, but that doesn't make a real vertex in the graph, which means that doesn't make a real circuit. All right. So that was the other 4 here. So I chose this 4. All right. Actually, now you can kind of predict the future a little bit. There's only one way to finish at this point. You have to go E to A. But if you like, you could go through the rest of the list. Can I use this 5? That would be this one, A to B. That makes it three-way at B, so that's not allowed. Can I use the other 5? That would be this one down here, D to C. That makes 3 ways also, so that's not allowed. Can I use the 7? The 7 goes A to E. Yes, I can use the 7. All right, and now I'm done. This is my final answer. And if I would like to say, often we like to say what's the actual weight of all these things. So I'll draw in the numbers. E to C was a 4, and then A to E was a 7. So here, my total weight is whatever. I didn't add it up on my paper. It's 10, 15, right? This is how you do the sorted edges procedure. All right? Now, sometimes I might say, use the sorted edges and write your answer as a circuit starting at A. So, sorry, I've written too big in here. Can I just move this guy over there? Total weight is 15, and the arrow. Sorry, I was going to write something over here. To write your answer, say starting at A or whatever, because it may be, on the test or on a homework or something. I might say, write your answer as a circuit starting at A. Well, this doesn't change any of the way that you did the procedure here. It just means when you get your final answer, you write this out in letters starting at A. And there's actually, so you could go A to D first and then B, C, E, A, or you could go A to E first. These are the same, they're just forwards or backwards, and I don't care which way you do it. So I will just say A, D, B, C, E, A. I'm just following the lines starting at A. A, D, B, C, E, A. You could have also written it the other way around, A, E, C, B, D, A. Those are equivalent. All right? But this is a little, some people, you might get thrown a little bit. If you see the question and it says, write your answer starting at A, you might feel like when you're doing the procedure, you need to start with A, but that's not true. The procedure is you do without any particular starting point or anything. It's just when you write your answer at the end, you write it starting at A. All right? Any thoughts or questions about this? I just got one right here for you to try. See if you can do it. Same procedure here. These are different numbers. I'm going to see how you feel. All right, can we talk about these? I hope that you got the same answer that I'm about to get. You should write them, the edges down in order. Now, actually, if you know what you're doing, really, you can just sort of look at all the numbers together. It's not always necessary to write them down in order, but it can be helpful. Anyway, I should begin by trying to choose the ones. There's a 1 here and a 1 here, and those are both legitimate choices. Neither of them makes a subcircuit or a three-way, so I'm going to pick the ones first. Next, I should consider the 2s. I have a 2 from A to B, and that actually is legal. That doesn't make a subcircuit or a three-way, so I pick the 2. And I also have a 2 from E to D, and I think that also is legal, right? So far, I have chosen, I'm getting lucky here. There's nothing that causes any problems. I've chosen the 2 1s and the 2 2s so far. All right, what about the 3s? I have a 3 here, A to E. That is no good because that makes three-ways at A and E, and it also makes a subcircuit A, B, E. So I can't choose that 3. I also, where's the other 3? B to C. That also makes a three-way at B and a subcircuit. So B to C is no good. I look now at the 4s. I see E to C. That is no good because it makes a three-way at E. But I see the other 4 actually is also bogus. I don't know why I said but. That makes a three-way at B, so can't use the other 4. And then we have 2 5s. The 5 across the bottom is the last edge that actually works. The other 5, D to A, would have made three-ways. So this is my answer. All right? I hope everybody got this same picture here. And I said specifically, use these sorted edges to find a Hamilton circuit starting and ending at A. I hope that this didn't throw anybody. This has nothing to do with the procedures that I've done so far. It's just about how I write the answer. I should write the answer starting and ending at A. So I should say it like A first, and then actually there's 2 ways to do it. I could go A to B, E, D, C, A. I'll write it that way. A, B, E, D, C, A. Or if you prefer, you could go the other way around, A, C, D, E, B, A. Those are the same answer, basically. Forwards or backwards, the same route. All right, this is the sorted edges algorithm. Anybody got questions about this? In my opinion, it's fairly easy to do. You should expect, this is going to be one of the test questions, and I hope it seems workable. All right, and it's really no more difficult if the graph is bigger. So if you turn the paper over, you will see one last example of a bigger one. So in this one, I'm saying find a good Hamilton circuit starting at A using the nearest neighbor and the sorted edges. So both of these are things that you'll need to do on the test. Maybe let's try the nearest neighbor. This is what we did last time. I hope you remember what we did last time. The nearest neighbor. So this is, really what I have here is sort of 2 separate things. So let's try the nearest neighbor first. I will just real quick review how the nearest neighbor works. So in this case, I have 6 vertices, A, B, C, D, E, F, in this arrangement. And if you recall from last time, the nearest neighbor means I said starting at A. So for the nearest neighbor, it actually does matter where you start. Starting at A, the nearest neighbor is the one where you just make the cheapest choice available from whatever point you're at. So from A, my choices are 10, 20, 15, 8, and 9. And I pick the 8 because that's how the nearest neighbor works. You start somewhere and you just make the cheapest available choice at each point. So from A, I'm going to pick the 8 first, which means go to E. That's for 8. And then from E, now I, again, make the cheapest choice available. My choices are 14, 15, 14, 8, or 11. The best, of course, I just came along the 8, so I can't pick the 8. The best of those options would be the 11 across the bottom. So that's there. Now from F, I can either go to B, C, or D, and those weights are 13, 7, or 12, so I take the 7. D. That's for 7. All right, this is the nearest neighbor. This also is not really hard to do. From C, I go, I can either go to D or B. Otherwise, I will make 3 ways at E or F. So is it D or B? 13 or 1? Definitely 1 is better there. And now to finish it off, actually the only way that I can go at this point without making three ways would be to D and then back to A. So that's a 15 and a 15. All right, that's the nearest neighbor procedure. And I added this up ahead of time. The total using this route is 57. And as we discussed last time, the nearest neighbor does not necessarily give you the best route. If you really want the best possible route, you have to do the brute force, which in this example would require like checking hundreds of different cases, which I would never ask you to do brute force for a big one like this. All right, that's the nearest neighbor. Anybody got questions about that? I hope that everybody remembers this from last time. Those of us who were here last time, real ones know, as they say. All right? I remember the real ones who came last time. Let's try the sorted edges on the same thing. That's what we were just talking about. So let's try, I got to scroll it. Are you worried about doing the sorted edges on a big one? It doesn't really matter much how big it is. I'll just make another copy here. Will it work? No. Yes. All right. So again, this time I don't care about where we're starting. Sorry, I have that circled permanently. I can't erase it. I can do this. Get out of there. Oh, I killed the A. All right. It's not worth it. Okay, anyway. Let's do the sorted edges. Again, can we try and do this one without writing all the numbers down in order? I mean, you can just look at all the numbers, right? And you just choose the lowest one, and then choose the next lowest one, and so on. If you like, you could write them all down, although there's kind of a lot to write down. What should I choose first? Can anyone see the lowest one available here? The one, yeah, the one at the top I should pick as my first choice. That is this edge here. All right. I don't mind scribbling on the picture, although maybe you guys don't have two pictures like I do, so maybe I'll write it separately. I picked the one anyway, so my answer I'll write over here, C, B, A, F, E, D. And I began by choosing the one up top, right? Can anybody say what's the next lowest one? You have to look carefully, make sure you don't miss any, but what's the next cheapest available edge?
7.
I believe it's the 7, right? I don't see any numbers less than 7, but give yourself a couple moments to convince yourself there's nothing less than 7. So the next one I pick is the 7. And the 7, of course, at this point is legal to choose. There's no three ways or subcircuits or anything like that. What should I pick next? I'm looking for the next lowest number available in the chart. I would say the 8, right? There's an 8 here. That is this edge. Is anybody bothered by the fact that this edge doesn't actually connect to what we've done so far? You should not be bothered. When you're doing the nearest neighbor, you actually do go one to the next in a sort of connected path. But when you're doing the sorted edges, you don't try to connect them up. They will naturally connect up in the end. You just have to sort of trust in the journey, right? This is not connected yet, but it will be. Okay, what next? I see the 9, and I think the 9 is the best I can do for the next choice, and it is still legal to choose the 9 at this point. Don't worry about this little triangle. That does not count as a subcircuit, like I said, because this is just crossing lines. That's not actually a real intersection point at a vertex. So that's a 9. Okay, what's next? The next number that I see is 10, but actually this 10 from B to A would make a three-way at A. So I X out the 10. Do I hear 11? There's an 11 at the bottom. Can I take the 11 at the bottom? No. Taking the 11 at the bottom makes a three-way at F, so that is not allowed. There's a 12. The 12 also would make a three-way at F. That would be here, and that is not allowed. There are 13s. There's a 13D to C, but that makes a three-way at C, so I can't do that. There's a 13B to F. That makes a three-way at F, so I can't do that. I see 14s. There's a 14D to E, and I think actually that one is legal. This 14D to E, that does fit into what I've got so far, without making a three-way or anything like that. The other 14 does not work. 14 would go, there's another one, B to E, but that makes a three-way out of E. Not good. And then there's a 15, D to B, and that'll do it. I forgot to write some of the numbers in. This, yeah, like so. I picked this 15. All right, this is the sorted edges procedure. If you feel better writing the numbers out ahead of time, you can do that. Although I would say once you know what you're doing, it's not really necessary. All right, this one I added up the numbers just. Oh, and what did I say? So the question actually said find a good Hamilton circuit starting at A. So here, of course, I didn't try to make it start at A, but I can write the answer as if I was starting at A. I will go A, F, C, B, D, E, A. Right? I'm just writing the answer as if I had started at A. You could, I might say write your answer starting at B. You would write starting at B. It doesn't matter. All right, and this one, the weight, I added these numbers up, is 54, which is different from the other one. So actually, in this particular example, the sorted edges gets a better answer than the nearest neighbor. Like I said, neither of these answers are guaranteed to be the best possible answer. The only way to get the best, to be sure that you got the best possible, is to do the brute force, which I would never do in this example, because it's too big. Maybe if I was using a computer, the brute force could work okay, but not by hand. All right. This is the sorted edges procedure. Anybody got questions about that? You should expect one on the test that looks, like this, I guess. I mean, you could even do a bigger one, although, to be honest, for me to make a picture like this in my computer, it takes me a few minutes. I'm not into making bigger diagrams than that with the numbers on all of them. All right. Excellent. Great. So this that's really all that needs to be said about the sorted edges algorithm. This was on our list number 31, I believe, or 32. It was number 31, the traveling salesman problem, sorted edges. I would like, so we have 20 more minutes today, plus, next time. That's enough time to do just one more, which is really just kind of a fairly simple variation on this, what we just talked about, although it's an interesting, different setting in which the same kinds of ideas can give you useful things. So this was, what we just talked about was number 31, which on the big list it's written like traveling salesman problem, sorted edges. That was number 31. I would like to add a new one. If you have your checklist on paper here, maybe you can squeeze this in at the bottom. So unfortunately, I already called the math chat question was number 32, which everybody got full credit for. And if I actually had a chat about your question, then you got 3 points on that one instead of 2. I would like to squeeze in, so I made up a new version of the checklist that you can print out if you want to, but I don't think it really matters. I'm going to move the math chat just because there's no real sense in having a number for it. I'm going to call that star now, and the new number 32. So on our test on Friday, there will be a question number 32, and I'm going to call it this, MST, sorted edges. It turns out there is another very common kind of real-life graph theory problem. Not the traveling salesman problem, it's something else, which has the abbreviation MST. I'll tell you what it means in a moment. But anyway, there's another very common real-world situation where the same type of sorted edges procedure lets you solve the problem. So that's what I would like to talk about just for our remaining time today and next time. And to be honest, it probably won't take, it won't even take all that time because it is just a variation on what we have been talking about today. I hope you don't mind me adding something into the list. So let's talk about this anyways. So this is another important graph theory problem. that does come up in the real world. And by real world, I mean it probably doesn't come up like in your own personal life. It certainly has never come up in my own personal life, but it is something that's important in a lot of real situations that some people have to deal with, like in their jobs or whatever. It is called, here's the MST. We call it the minimal spanning tree. The minimal spanning tree. And really, as a problem, sort of the problem is finding a minimal spanning tree in a weighted graph. All right. So we got 15 minutes today. I should be able to explain what all those words mean, and then we'll talk next time about how to actually do this using some kind of sorted edges type procedure. So let's talk first about spanning trees. Maybe we'll just take this kind of one word at a time. So first of all, let's talk about a tree. A tree is a special kind of graph. By tree, I mean something, you can imagine something like a family tree as a graph, right? Like each person is a vertex and there's like branches that go down to other people. The important thing, like what makes a tree, well, you should be imagining something like this. Right? This is a tree. It's a graph. I mean, it is a graph, right? Because it has vertices and edges. I was just making that one up. The important thing about a tree is that you have sort of each vertex has certain kinds of branching to it. What makes it a tree is this is the real definition. A tree is a graph with no loops in it. Right? Like you can't make a circuit in this graph unless you just go back exactly the way you came. Like if I start up here, there's no way to follow edges in the graph sort of making a loop and coming back where I started, except for just literally following back the same way that you came, and that doesn't really count as a loop at all. It's a graph with no loops in it. So that is a tree. Here's another example of a tree. This one I didn't draw it vertically, but you know, that's a tree, right? It's a graph where there are no big loops in it. These are both examples of trees. So this is a tree, right? Here's, just for the sake of completeness, here's an example which is not a tree. That's not a tree because of this thing, right? This thing here makes it not a tree because this has there's a loop right there. So this sort of thing right there, this is not a tree. A tree is a graph which does not have any loop type parts in it. All right? Okay, what about a spanning tree? What is the meaning of that? So inside a graph, a spanning tree is a tree which meets every vertex. So what this looks like is, for example, I'm going to draw a big grid graph here. And so that's my big graph. When I say spanning tree, I mean you're going to draw sort of another graph inside of this one. And the thing that you draw inside of this one should be a tree which meets every vertex. So that could look something like, and I'm going to do this just by scribbling edges, the way that we did when we draw sort of a Hamilton circuit. Here's an example of a spanning tree in this graph. I'm just making this up as I go. It is not hard to find spanning trees. How about that? Like that, like that. I believe this is a spanning tree. I hope that you can see those lines all right. Maybe I'll just thick them up. probably easier to see. But if you're drawing by hand, you can scribble them like that. All right? What I drew in red is a tree because there are no sort of closed up loops in what I drew in red, and it does meet all the vertices of the original graph. All right? So that thing that I drew in red is a spanning tree. So the red is a spanning tree. All right? It meets all the vertices. And it's a tree because it doesn't have any kind of closed up loops in it. All right. What's the point of a spanning tree? Actually, this comes up all the time in real life. If you imagine, for example, if you imagine that this was like a neighborhood block of houses, and you need to lay down like water pipes so that you get water to each house. Actually, the way to do that is in a spanning tree. If you're putting down the water pipes, it's important just because of the way that like pipes work that you don't have a loop in your network of pipes because you don't want the water to just like go around in circles all the time. The idea is, well, if you want to effectively build a network of pipes that make it to every house, they must be arranged as a tree because you don't want loops in it. And if you want it to get to every house, it has to be a tree which meets all of the vertices. That is a spanning tree. The exact same thing is true for like electrical wiring or any kind of thing like that. Electrical wires do not make circuits because that would mess up the way that the electricity is flowing. So spanning trees, I will just say in real life, this comes up in with things like, you know, wiring houses together in a neighborhood, but also much more complicated things like, you know, everybody knows like a computer chip consists of like millions of tiny little microscopic connections. Those connections, generally speaking, you want them to be arranged in certain cases, they have to be arranged like spanning trees. So in real life, this comes up with wiring, pipes, etc. Any kind of scenario which is like that. You have to arrange these things in trees. This is different from, say, a Hamilton circuit, which I also drew with sort of red lines, but this doesn't make a circuit. A Hamilton circuit would be a circuit which meets every vertex. Is different from a spanning tree, which is a tree which meets every vertex. All right, this is a spanning tree. It comes up often. Here, I just want to draw a couple more examples. How about, generally speaking, a typical graph will have like many possible different spanning trees. Like this one here, I could draw a spanning tree, could look something like, I'm gonna get the thickness on, something like this. That's a spanning tree, right? It meets every vertex and it is a tree. What you draw as your spanning tree cannot have any loops in it. So it would be wrong. You know, like I said, there are many ways you could have done this, but like if you had instead drawn it like that, I just added this edge right here, that would be wrong because now I have a loop in it. Not allowed in a spanning tree because that wasn't a tree, what I just drew. All right. Let's discuss what's the difference between a Hamilton circuit versus a tree, because there are some similarities. So this one, if I were to draw the same graph, I don't want to do that. Can I just say, oh, I'm still thick here. Hamilton circuit has no three-ways, no subcircuits, right? That's what we've been talking about the past few times. What's the difference with a spanning tree? Just by looking at this, you can say, is a spanning tree allowed to have three-way intersections? Yes, it is. That one does have, this has a four-way, in fact. Is a spanning tree allowed to have a subcircuit? This one doesn't. But what if I did? Like, what if I actually also took this edge? Is that a problem? for a spanning tree, would that still be allowable? I think actually that is a problem for a spanning tree. This is no longer a tree if you close up this this part of it here. So spanning tree, this is really the only difference. A spanning, the thickness. The spanning tree can have three ways, but still no subcircuits. Right? Because a tree is not allowed to have any kind of loops in it, so it can't have any circuits at all, subcircuits or big circuits, right? A spanning tree can have three-way intersections, but still no subcircuits are allowed. And so I will just say, generally speaking, maybe I will leave you for today with these thoughts. So finding spanning trees generally is like finding Hamilton circuits, although much easier. But three-way intersections are allowed. That's really the only big difference. It's much easier than finding Hamilton circuits. And in particular, you can still do something like the sorted edges. Remember the sorted edges, what we did, 20 minutes ago? It involves picking edges, and every time you make sure it doesn't make a subcircuit and it also doesn't make a three-way. You can do exactly the same thing, but you just allow for three ways, and you get a sorted edges for minimal spanning trees. We'll do some examples of that next time, and I think that will do it for us. All right, let me know. We do have homework due tomorrow as usual, so let me know if you want to chat about that. I would be happy to. And if you weren't here last time, come and get a printed out copy of the homework.